This video is going to be on analyzing graphs of derivatives, and we are going to have several graphs on here, so if you're not using graph paper, you probably legitimately need some. So, analyzing graphs of derivatives. Okay, so if you are given the derivative, we're given the graph of the derivative, and you need to find where the original function is increasing. This would be the part of the derivative graph that is above the x-axis. And the reason that we're going to look at the part of the graph, the derivatives graph that's above the x-axis, is because this is where f prime of x is greater than 0. And f prime of x is describing the slope of the original graph, and so that would be where the slope of the graph is positive, and positive slopes are where it's increasing. So to see where the original graph is decreasing, you're going to look below the x-axis on the derivative, and the reason for this is because when the derivative is less than 0, that means that you have a negative slope, and negative slopes is where the original function is decreasing. If you want to know where the function has extrema, so local mins and maxes, absolute mins and maxes, you need to look at the x-intercepts of the derivative. And the reason for that is that the derivative equals 0 at those points. There's a horizontal tangent there. And we know that horizontal tangents, or slopes of 0, happen at high points and low points. So that would be x-intercepts of the graph. If you want to know if the original graph is concave up, then on the graph of the original, you need to look to see where the derivative has positive slope. Another way to say this is to see that it's where it's increasing, where the derivative is increasing. And the reason for this is that where the derivative has positive slope, we would describe the derivative of the derivative, which is the second derivative, as being greater than 0. So we know that the slope of the derivative, when that is greater than 0, that means that it's increasing or it has a positive slope. The original graph is concave down when the derivative has negative slope, or is decreasing. So that's two different ways of saying the exact same thing. Negative slope and decreasing are the exact same thing. And the reason that that makes sense is because concave down happens when the second derivative is less than 0. And the second derivative describes the slope of the derivative. So when the slope here is negative, then that means that the derivative has negative slope, that it's decreasing. All right? And then last, if we want to find the points of inflection on the original graph, we want to see where the derivative switches from a positive slope to a negative slope. So these two slopes, when those switch, because that's the switching between concave up and concave down, which is the definition of a point of inflection, or from negative to positive. And the reason that works is because the second derivative equals 0 at those points. So these are maxes or mins of the derivative function. All right. So the left side over here, this describes the function itself, so f of x. This part over here describes the derivative. Okay. So for these examples, we just want to make sure that we can find all of those things that we're looking at. So I'm going to give you a graph of the derivative. So given f prime of x, find the increasing and decreasing intervals, the extrema, the concavity, and the point of inflection for the original function. So the first point we're going to graph is -2, +2, and then the point -1, 0. And we're going to have this graph look like this. So it's going to look coming down. And then we've got the point 1, -2, and the point 3, 0. And the graph looks like this. And then we have the point 4, 1, and the point 5, 0. Looks like that. And then 6, 1, 2, 3, 4, 5. And then the point 6, 1, 2, 3, 4. So 6, -5. And the graph is going to go down like this and then stop. And I did not mean to make that look like a vertical tangent line. So maybe if you want to fix that curve so it doesn't quite look like that, you can. But that was accidental. You don't have to fix it if you don't think it's going to mess you up. Okay. So if we want to see where the original function was increasing, then we're going to look at the parts of the derivative that are above the x-axis, because those are the parts where the derivative is positive, greater than 0. So since the derivative means the slope of the original, that's why we would use those positive values. So we're going to say the original graph was increasing from -2 to -1, because this part of the graph is above the x-axis. And then also over here from 3 to 5. The graph is decreasing from -1 to 3 because it's underneath the x-axis. And it's decreasing from 5 to 6. The extrema, the maxes and mins, are all these x-intercepts, because this is where we switch from increasing to decreasing. So if I picture this x-intercept right here, it was increasing and then it was decreasing. So if I am picturing my original graph, it went from increasing to decreasing, and so that's a maximum. So I have a maximum at -1. And actually here we don't have a function to plug it into to find the two coordinates, so I'm just going to say x equals -1. Alright, and then here we switch from decreasing to increasing. So switch from decreasing to increasing means that that is a minimum value. So we have a minimum at x equals 3. And then here we're switching from increasing to decreasing again. So increasing to decreasing means that we have a maximum at 5. Alright. Next we want to look to see where the graph is concave up or concave down. And so here we have to consider the slope of the derivative, whether it's decreasing or increasing, because when we do that, then we'll know where the second derivative is positive or negative. So this graph is decreasing from -2 to 1, and so the original graph would be concave down, so -2 to 1. And then it's increasing from 1, 2, 3, 4, 1 to 4. And then it's decreasing from 4 to 6. And then the point of inflection, again, just like the max and the min, I can't write the actual coordinates for that, but I can write the x value. So I can see it switches from a decreasing slope to an increasing slope at x equals 1, so that's a point of inflection. That's where the concave up and concave down switch. And then here it's increasing to decreasing, and so the other point of inflection would be x equals 4. Okay, so we're going to do another example of this. Well, I'm going to go up and call this example 1. This will be example 2. So we're going to start the graph at 0, 0. And then it's going to go down 1 to the right 1, and then to the right 1 up 1. And then over 1 up 2, and then back down again. Let's keep that going to an x value that is easy to say. So we'll say this continues up until we get over here. Okay. So the increasing part of the original function happens when this derivative is above the x-axis. So this graph is increasing from 2 to 4. 1, 2, 3, 4, 5, and then from 6, 7, 8, 9, 10, and then 6 to 10. This graph is decreasing from 0 to 2, and 4 to 6. That's it. We've got maximums and minimums happening. So the graph switches from decreasing to increasing at x equals 2, so that's a minimum. It switches from increasing to decreasing at x equals 4, so that's a maximum. It switches from decreasing to increasing at x equals 6, so that's a minimum. And then those are the only switches, so that's the only, or those are the only extrema we would find. Next we'll look at concave up and concave down. So the graph is decreasing from 0 to 1, so that's concave down. And then it increases from 1 to 3. And then it decreases from 3 to 5. And then it increases from 5 to 7. And then it decreases from 7 to 8. And then increases from 8 to 10. And then last, our points of inflection are where the graph is changing from increasing to decreasing. So it changes here at 1, and it changes at 3, and it changes here at 5, and it changes at 7, and then it changes at 8. Alright, for the next example, we are going to sketch the derivative given that we have the original function to start with. So here is our original function. So I'm just going to go through and find all of that information we usually look for, and then we can use it to sketch the derivative. So this graph is increasing from -4 to -2, and then it is decreasing from -2 to +2, and then it starts increasing again from 2 to infinity. When we sketch our derivative, it doesn't matter which point is a max and which point is a min. They show up the same way, and so I'm just going to go ahead and write both of these down. X equals -2 and +2, and the y coordinates don't really matter. And that's something that we can talk about tomorrow, so you might think about that, why the y value doesn't matter. The concave up and concave down. So the graph is concave up from -4 to 0, or -infinity to 0. And then it is I switched those. And then it's concave up from 0 to infinity. And then the point of inflection, where it switches, is at x equals 0. Okay, so let's go ahead and interpret each of these things. If it's increasing on these intervals, then we're going to say on those intervals it's above the x-axis. So from -4 to -2, and from 2 to infinity, we are above the x-axis. We are below the x-axis from -2 to 2. We're going to have x-intercepts. It's going to cross from being above to being below, and vice versa. When x is -2 and x is +2. We're going to say that the graph is decreasing, so it's concave down. It's going to be decreasing from -infinity to 0. It's going to be increasing from 0 to infinity. And it's going to have extrema. It'll have a max or a min. I guess we could figure out if we want which one it is if we wanted to. It's going to have an extrema, some sort of local max or min at 0. So now we can go ahead and sketch this. So I know I have an x-intercept at -2 and +2. I know that the graph is above the axis on either side of here and here. I'm kind of sketching it because I don't want to mess anything up. I know the graph is increasing from 0 to infinity and decreasing from -infinity to 0. And I know it has some sort of extrema. It must be a minimum down here. So I'm just going to say, and it doesn't matter how far down you go. And this fits the graph. So if we look above the x-axis, on these intervals over here, below the x-axis in between, we have our x-intercepts. We are increasing from 0 to infinity, we are decreasing from -infinity to 0, and we have the extrema right there at 0. So I'm going to go ahead and label this. This is f of x, this is f prime of x. We're actually going to jump down here and graph the second derivative while we're at it. So, if you guys recall, concave up and concave down describe where the graph is increasing or decreasing. So if this derivative is increasing from 0 to infinity, then that means that the second derivative is above the x-axis for those values, and it's below the x-axis for the decreasing values. And the reason that I could know that from the original function is because of the definition of where we find our concave up and our concave down. We always found those. Concave up was where the second derivative was positive, Concave down was where the second derivative was negative. So now we're going to say it's positive above the x-axis, it's negative below the x-axis. And then the point of inflection is where it would switch from concave up to concave down. In this case, it's going to be where it switches from above the x-axis to below the x-axis, and so that point of inflection is actually going to give us our x-intercept. So our x-intercept is going to be x equals 0. So the second derivative would look like this. From 0 to infinity, we are above the x-axis. From negative infinity to 0, we are below the x-axis. We have an x-intercept of 0.